Hi all, I am Vishnu Deep. So I am going to explain the hardware implementation of LeNet neural network on an FPGA. This is the final project, mini project 3 for double EE278 from San Jose State University. The instructor is Professor Chang Chu, and this is going to be dealing with the digital design for AI and DSP. So coming to the presentation, uh, this is the LeNet implementation of on FPGA. Basically, LeNet 5 is one of the primitive convolutional neural networks which is present and usually used for image processing sorts of techniques. So coming to the aim of this project, the aim of this project is development of a LeNet interface engine for image processing and its applications. So the device used is going to be Zinc family FPGA. And so we are going to go with the Zinc 7000 FPGA family FPGA, and the part number is as follows. So the language used is it's going to be completely coded in Verilog HDL, and I'm going to be using Xilinx Vivado for this. Mm. So coming to the architecture which I have implemented, so basically the LeNet architecture, it consists of an input layer. An input layer consists of 32 cross 32 grayscale image input. The next layer after the input layer is going to be convolutional layers, which are going to extract the features from the given inputs. And once these features are extracted, they are going to be pooled in layers, and this is going to be done in the pooling layers. And once the pooling layers have the complete set of information, or the data in terms of bits and bytes, these bits and bytes are going to be read by fully connected layers, and they are going to formulate a predicted value, and the predicted value is going to be given out to the output layer. So coming to the implementation of this project on Vivado. So we'll have to create multiple modules and instantiate them in a top module for the Vivado to function effectively. And that is a good practice of implementation as well. So this is going to be the implementation strategy which we are going to use. There, uh, since there are many functions which are going to be performed, each module written in HDL is going to be dedicated for that specific operation. So, for example, the systolic array wrapper is going to be solely used for matrix multiplication. The ReLU module is so ReLU is basically a function which is going to be used as an activation function, and the max pool 2 cross 2 is going to be used for pooling operations, and fully connected layers is used for weight handling in the network. And there's a top module which is useful for integration of all the other modules. So we are going to have two layers. We are going to have two layers in this network. So the ReLU module is going to be repeated twice. The max pool layer is going to be repeated twice. I can show you the Vivado implementation in the later stage of this video for better understanding. So coming to the working of this entire project. So an input of 32 cross 32 image is processed through the convolution layers present in the systolic array wrappers. So this input is being fed into the project by our test bench, and the ReLU module and the max pooling layers are one of the important modules which help in the extraction of the features from the given input. The features include, in terms of electrical engineering, is nothing but zeros and ones, which the quality of the image is measured in terms of zeros and ones, and the characteristics, it's also measured in terms of zeros and ones, and different patterns create different binary files for this, and ultimately this is given out as a signal. So the fully connected layers classify the features, and we have 10 different output properties defined in the design, and it is going to give out one particular property. So each particular property is going to be mapped for certain features. The network operation is also dependent on the weights. Since we are talking about convolutional neural networks or any other neural networks, designing of weights is very much important in such aspects. So coming to the weights, we are going to use pre-trained weights. Now, the pre-trained weights are nothing but they are going to be fed to this design from the test bench. I don't have a specific hex file for the weights since I'm using HDL, purely HDL. I'm going to use them in the, I'm going to generate different patterns of weights and going to feed them into the DUT by the test bench. So I was successful enough to implement this on the FPGA, and I got the synthesis to pass as well. So this is going to be the implementation of the uh, implementation in terms of block design. So the big unit which is seen here is the RTL return, and this is the systolic array. This is the systolic array, and there are many more IPs which are being used. For example, the clock divider and the processing system and many more. And the outputs of the systolic array are given out as pins here, and the output valid is going to be a flag which tells us about the validity of the given output and many more. This is going to be the pooling layer buffer, whatever we are going to use, so on. This is going to be attached in the Xilinx Vivado project, which I'm going to be updating. So coming to the implementation, the RTL consists of various modules, as mentioned earlier. So this is the synthesis report. So I'm concentrating on the DSP elements, basically DSP mapping. So since this is the design is based on floating point multiply and accumulate, this is the mapping which happens, and these are the operations which are performed. And going to the test bench. So the features of the test bench are clock generation, driving the input stimulus, assigning of weights, etc. So clock generation, as it's self-explanatory, a clock is signal is generated, and we have defined a period of 10 nanoseconds in the entire simulation. Next, the input stimulus, various test cases are applied, including uniform weights, sequential values, edge cases of all zeros, all ones, and using the randomized function, we also generate random values of the input stimulus. And the weight assignments, the weights have to be assigned to the fully connected layers. So there are 3 fully connected layers in the LeNet implementation, which I've done. So namely FC1, FC2, FC3, they're all instantiated, and the weight assignment is going to directly impact the fully connected layers, and with the assignment of the weights, we can be able to derive the output, because the processing takes place, and it is going to give out a certain value. It is going to give out the output, certain output parameter from 0 to 10. So the predicted class and the output signals are monitored to verify the correct predictions from the neural network. And we also simulate the edge cases. Weight handling tasks, again, like I said before, is going to be handled by the test bench. So I was successful in getting the simulation done. So this is the simulation where we give the input of all cases. So this is gone to the end, showing the FFFF, the highest value. It starts from a lower value. So once we have the output signal valid, this results in this result implies in giving this results implies in saying that the signals generated by the test bench and the signals passing through the DUT is good enough, and it is passing. So these are the weights, the weights which are values of the weights which are handled in the FC1, FC2, and FC3. So the weight values vary throughout the test bench, and these are one of the random weight values which we have fed into the test bench. So the FC1, 2, 3 are the fully connected layers, and you can see the values here in hex. So for this project, I used multiple references. Of course, the LLM assisted me as well. And basically, the floating point Mac unit, which was created for the mini project 2 of the same course, EE278 Digital Design for AI and DSP, and the code which was C code in the spec in the technical specification of the mini project 3 provided by Professor Changchu uh, are mainly used. So now let me give you a demo of how this works. So coming to the instantiation portions and the project hierarchy. So this is going to be the top module which we have. We have one convolution layer here, which consists of a systolic array and four cross performing 4x4. And these are all the floating point MAC units which we have here. Uh, and coming to the and this is the relu1 function which is responsible for the activation here. So just a brief introduction or just a brief explanation of the relu. So relu is a rectified linear logic. So this function takes helps in processing the data only when we have the input which is 0 or above and doesn't help in processing the negative data. And this is the pool where we can pool all the data. Similarly, we have a convolution layer 2 with the similar structure, and these are all the fully connected layers which is developed by the systolic array wrapper which we have here. So all these are the codes RTL written. This is the LeNet forward, the top module. This is the systolic array wrapper, which acts as the floating point MAC. And this is the coming to the test bench. This is the test bench which we have, and it tests about 4 to 5 cases. So these are going to be the weights inputs, weights for the fully connected layer 1, 2, and 3, and it is generated here. So we have some of the lengths which are fixed for the sake of the simulation. So coming to the block diagram. So this is the block diagram which was created, and hopefully it is visible. Yes. So this is the block diagram created and created to demonstrate the implementation of the RTL which we have done. So coming to the simulation, we have this is synthesizable. Right now it is out of date because I've updated stuff. But coming to the simulation, so I'm running behavioral simulation. Yes. So the behavioral simulation output results are as follows. So this is going to be the input image which we have, and these are the weights which vary from these are the weights which vary from all these 0 to 6399 values in so each connected layers have a fully connected layers have a different weights which we have fed, and these are going to be the weight length magnitude of the weights which are going to be fed here. So the above two signals are the clock and reset, and based on that the behavior of the entire system varies. So this is a successful implementation, I would say. And thank you.